Welcome to the Robotics Brief. I'm Alex.
And I'm Sam, glad to be here as always.
Today, we're looking at a fascinating paradox. The industry is all in on giant models, massive data sets, and centralized everything-in-one-box solutions. Yet, a lot of the cutting-edge research we're seeing this week points in a very different direction. It's almost like the academic frontier is moving towards highly specialized, context-aware, and continually adapting systems, even as the commercial world scales up.
Yeah, it's a weird disconnect, isn't it? Because on the one hand, everyone wants to replicate the success of large language models in robotics. More data, bigger models, generalize everything. But then you look at these papers and they're saying, no, the real world is messy. It's dynamic. You need to adapt on the fly, use obscure sensor inputs, learn continually. It's like two different philosophies of how robots should operate are diverging.
Exactly. It's not just about getting a robot to do a task once. It's about doing it robustly, repeatedly, and flexibly in an environment that's constantly throwing curveballs. And that requires a kind of intelligence that a fixed pre-trained behemoth might just not possess.
Right, because the physical world isn't static text, it's always changing.
So let's dive into that. Our first story, Scalable Behavior Cloning with Open Data, Training, and Evaluation, or ABC, feels like it sits right at the intersection of these two trends. They've built the largest open-source teleoperation dataset to date, 130,000 episodes, 3,500 hours of data, 195 tasks. That's a huge undertaking, openly released.
Yeah, and that's the part that catches my eye, open source. We've seen so much emphasis lately on proprietary data, closed models, everyone hoarding their secret sauce. This team is just throwing it all out there. Hardware setup, training infrastructure, simulation pipeline, the whole 9 yards. It's a genuine community effort.
And they specifically say it's for manipulation. Not general-purpose omni-robot tasks, but dexterous manipulation. The scale of the data is impressive, but the specificity is also a key feature here. They're not trying to solve every robotics problem, just a very complex subset of them.
Which, honestly, is where I think a lot of the real breakthroughs are going to happen. You can't just scale up a general-purpose model and expect it to magically pick up a fragile object or assemble something complex. Dexterity is a whole different ballgame. My question is, how much of this dataset is going to be truly useful across different hardware? Because teleoperation data, while great, often embeds the quirks of the specific robot used for collection.
Well, they do release simulation data too, and a co-training recipe that they say produces correlated sim-to-real evaluation. So they're trying to bridge that gap. But you're right, Sam. Real-world data always has those hardware-specific nuances. My read is that this isn't just about the data. It's about establishing a new benchmark, a new common language for comparing manipulation systems. It sets a high bar for open-source contributions.
Yeah, but how many labs can actually replicate their accessible hardware setup and then collect 3,500 hours of data? Accessible for a big university lab might mean something very different for a small startup or an individual researcher. The barrier to entry for using this data might be low, but for contributing to a dataset of similar scale, it's still pretty high.
That's a fair point. It definitely lowers the hurdle for development and evaluation, but creating similar datasets is still a massive investment. Shifting gears a bit, let's talk about continual robot policy learning via variational neurodynamics. This one really speaks to the dynamic nature of the real world, something we touched on earlier. Robots don't operate in a vacuum. Batteries drain, parts wear, environments change.
This is what I was talking about. Most learning-based controllers are trained once and then deployed as if the world stands still. This paper directly attacks that limitation by building a framework for continual learning. It actually uses real-world experience to improve policies.
The key here is hidden and recurring dynamics. They're not just adapting to a completely novel situation. They're learning to recognize patterns in how the robot's dynamics change over time, like how a battery draining changes its torque response, or how a grippy surface degrades over repeated contact. It's a much more nuanced view of adaptation.
I appreciate that they're trying to move beyond the idea of a fixed model. It makes so much sense, Alex. A robot is an embodiment. It's constantly interacting, and those interactions change its internal state and its external environment. Why would you ever expect it to just stop learning? It's like designing a human and then telling them they can't have any new experiences after age 5.
Exactly. The idea that a robot can learn a condition-aware dynamics model from real state action trajectories, that's powerful. It's not just adapting the policy, it's adapting its understanding of how its own body and the world around it behave. It creates a much more robust system, less prone to failure when conditions inevitably shift.
My skepticism here is around the complexity of hidden and recurring dynamics. How many different hidden dynamics can it really track and adapt to effectively? The real world isn't just a few recurring patterns, it's an infinite combination of subtle changes. Are we talking about adapting to 5 different scenarios, or genuinely generalizing to unknown, never-before-seen dynamics? Because the latter is a much harder problem.
They talk about a variational neurodynamics model, which hints at some probabilistic modeling to handle uncertainty. It's not about identifying every single change, but learning a distribution over possible dynamics. But you're right, Sam. The real challenge is scaling that to truly novel shifts, not just recurring ones. That's the holy grail of robust, autonomous systems, isn't it? Next up, ViBACT, Vibration to Actions for Contact Reactive Robot Dexterity. This one really caught my attention because it's about a completely different sensor modality, vibroacoustic signals from piezoelectric microphones embedded in a robot hand.
Yeah, that's wild. They're using sound to figure out what the robot's fingers are doing when they're interacting with objects, especially when vision is occluded. It makes total sense. Humans rely heavily on haptics and proprioception for dexterity, and sound is a part of that.
But here's the kicker. Vibroacoustic signals are notoriously difficult to simulate accurately, so they can't just do sim-to-real learning directly. Instead, they bridge it using a shared physical representation of contact and slip. That's a really clever workaround. They don't try to simulate the sound, they simulate the underlying physical events that cause the sound.
That's a smart hack, honestly. Instead of trying to recreate the raw sensor data in simulation, which is a nightmare, they extract the meaningful information, contact forces, slip, friction, and make that the common ground. It's like focusing on the physics, not the pixels or the audio waveforms. This makes the simulation more directly relevant to the real-world problem.
And the applications are huge for contact-rich tasks like assembly, grasping oddly shaped objects, or even delicate handling. When you can't see what your fingers are doing, feeling, or hearing in this case, those subtle interactions becomes critical. This is a very specific type of specialized intelligence.
I just wonder about the robustness of these piezoelectric mics in a real industrial setting. They're often quite fragile, and if you're embedding them into a robot hand that's constantly making contact, how long do they last? And how does temperature, humidity, or even just ambient factory noise affect the signal? Because those things will change the sound of contact.
Yeah, that's a practical concern. The paper doesn't explicitly address long-term durability, but for research, it demonstrates a powerful concept. It's about opening up new sensory pathways for robots, not just perfecting existing ones. And using these non-visual cues could be game-changing for complex manipulation. It's another example of tailoring the approach to the specific problem, rather than trying a one-size-fits-all solution.
World action models enable continual imitation learning with recurrent generative replays. This is another take on continual learning, but through a very different mechanism. It's about robots essentially rehearsing past tasks. This sounds a lot like memory, doesn't it? The robot doesn't have to store all the original human demonstrations. Instead, it uses a world action model, a WAM, to generate pseudo-replay trajectories. It's creating its own training data, essentially. Right. WAMs can predict future visual observations. So instead of just predicting actions, they can generate an entire sequence of what the world should look like given a certain action. And they leverage this generative capability for regen, which synthesizes these pseudo-replays. It's a way for the robot to remember how to do old tasks without literally storing the memory of how it was taught. That's critical for scalability. If every time you taught a robot a new task, you had to keep all the original demonstration data, you'd quickly run into storage and computational limits. Being able to generate synthetic replays is a huge step towards making continual learning practical in the long run. And it's not just about storage. It allows the robot to learn new tasks while still practicing old ones, preventing what they call catastrophic forgetting. The robot can recursively query the WAM to synthesize these replays based on prior task instructions. It's almost like it's replaying its own memories, conditioned on what it's trying to achieve. My main concern here, Alex, is the fidelity of those pseudo-replays. How accurate are they? If the WAM generates slightly off trajectories, is the robot going to be reinforcing incorrect behaviors? And how does that drift compound over many iterations of continual learning? You could end up with a robot that's confidently doing the wrong thing. That's a real risk, Sam. The quality of the generative model is paramount. They claim experiments show it works well in both simulated and real-world scenarios, but the real world here is usually still fairly controlled. The problem of generating perfectly realistic, unbiased replay data is a hard one, and if it fails, the whole system could degrade over time. It's a fascinating concept, though, this idea of generative memory for continual learning.
Finally, router VLAN
turning smoke tests into supervision for heterogeneous VLA selection. This one is about how robots pick the right policy in the first place, especially when they have multiple options.
Okay, so this is about decision-making at a higher level, right? When you've got a bunch of different vision language action policies, VLAs, for different tasks, how you decide which one to use for a new task without just trying them all out.
Exactly. Robot teams often do smoke tests where they run candidate policies and then just pick the best one. Router VLA takes those initial probes, those failed or successful trials, and reuses them as supervision to train a router. This router then learns which VLA is most likely to succeed given the current situation.
So it's about making those initial, often discarded, failed attempts useful. It's essentially learning from its own mistakes, or the mistakes of its component policies, to make better selection choices in the future. I like the efficiency aspect here, not wasting data.
And the results are pretty compelling. They saw a plus 14.64 percentage point gain in held-out success. That's a significant jump just by using existing pre-deployment evaluation rollouts more intelligently. It's not about improving the individual policies, but improving the selection of which policy to use.
That's key, because a lot of effort goes into making better individual policies. But if you can't reliably pick the right one for the job, then those improvements are moot. This is a meta-learning approach, learning how to learn, or rather, how to choose.
It speaks to the complexity of deploying robotic systems. It's not just about having good component parts. It's about having a smart orchestrator that knows when and where to apply them. It's an admission that no single VLA is going to be universally optimal.
But it relies heavily on the quality of those smoke test trials. If those initial probes are biased or don't cover the full range of real-world conditions, then your router is only going to learn from an incomplete picture, and then you're just propagating the bias. It's a smarter way to use bad data, but it's still data-dependent.
That's true, Sam. The quality of this supervision is crucial, but it's an intelligent way to leverage what would otherwise be throwaway data. It shows that even small, seemingly insignificant evaluation data can be turned into a powerful learning signal. So when we look across these papers, Sam, what's the thread you're seeing? Because it feels like a move away from the bigger model, more data, solve everything approach.
Yeah, I think it's about specificity and adaptation. We're seeing systems that are highly specialized for particular problems, dexterity, dynamic environments, specific sensor modalities, and that are designed to continually learn and adapt, rather than being static once deployed. It's less about brute force, more about elegant, context-aware intelligence.
I'd agree with that. It's almost like a shift from trying to build general intelligence to building robust intelligence. How do you ensure your system works reliably, not just in the lab, but in the chaotic, ever-changing real world? And the answer seems to be by embracing that chaos, not trying to eliminate it.
Right, by designing systems that expect change and are built to evolve.
Which leaves us with this question. How far can these specialized, continually adapting systems scale before they hit the limits of their architectural specificity? Are we seeing a future where robots are bespoke learners for every scenario, or will these ideas eventually feed back into more general architectures?
That's the million-dollar question, isn't it?
That's it for the Robotics Brief this week.
Thanks for tuning in, everyone.
See you next episode. Take care.